Hi, I'm Dan Poppy, the producer for the Analytics Engineering Podcast. Before we get to this episode, I wanted to invite you to join Tristan May 28th at the 2025 DBT Launch Showcase for the latest features landing in DBT to empower the next era of analytics. Register now at getdbt.com. We'll see you there.
Welcome to the Analytics Engineering Podcast, featuring conversations with practitioners inventing the future of analytics engineering. In this episode, I speak with Wolfram Schulte. Wolfram is a distinguished engineer at DBT Labs. He joined us via our recent acquisition of SDF, where he was co-founder and CTO. Wolfram goes very, very deep on databases, compilers, dev tools, and a whole lot more. He spent close to 2 decades in Microsoft research and several years at Meta building their data platform. One of the amazing things about Wolfram is his love of teaching others the things that he's passionate about. Put him in front of a whiteboard, and he transforms into a professor. And so today, I ask him to put on his professor's hat and school me on the internal workings of data systems. We talk about SQL parsers, compilers, execution engines, composability, and the world of heterogeneous compute that we're all headed towards. While some of this might seem a little sci-fi, I truly believe that the world we discuss on this episode is right around the corner, and Wolfram is inventing some of the tech that's going to get us there. Without further ado, let's get into it. Wolfram, welcome to the Analytics Engineering Podcast.
It's really great to be here with you. Thanks so much for the invitation.
You and I are kind of smiling on this end of the camera because we know something that everyone else may not know. But you joined DBT Labs recently via an acquisition. We joined forces back in, I guess it was the official close date was December 31st. And we've since done a lot of interesting work that we've shown to the community in some different ways. I'd be curious, and this is, there's no wrong answer to this, but I'd love to hear in your words, why does the DBT plus SDF match make so much sense to you?
In any good team, you want to bring different capabilities together. And I think what DBT has done amazingly well is in some sense adopting software engineering principles for the data engineering community that includes writing models, introducing versioning control, introducing abstractions with libraries. And so, since you were the first and and therefore also the best, by definition, you got a huge following because there was such a great need. So I think you built up a great community. All your decisions were, in some sense, informed by the best practices in software engineering and then translated into the data engineering community. And you did not only get great following, but in some sense, bigger and bigger companies adapted your technology as well. So suddenly, you do not only get, in some sense, love, but you also get pain due to scale. So where do I come from? I come from, I worked in big corporations, Microsoft and Facebook. And so most of the problems is dealing with scale. So everything works in the small, but as soon as you scale to whatever, millions of users and millions of tables, nothing works as before. And so you have to turn on different knobs in order to make things work as well as in the small scale. And so coming from that background, we built in some sense core technology for understanding SQL, for scheduling workloads. But we didn't have, as a startup, the community, the breadth, the engagement, the excitement. We had first users that were super excited, but that doesn't necessarily translate into a business model. So we would have to build up, in some sense, a sales organization and marketing. And so DBT has all of that, and it has the right design principles that we follow as well. And it had a need for scale. So if you could get together, could that be a match made in heaven? I think so. And that's why we're here.
I love that. You started to talk a little bit about your personal background. I got to spend some time with you in the early days after the two companies came together, and I learned a little bit about your career journey, and even all the way back to, is it fair to call it a monastery in Germany?
Yes, yes, yes,
Can
yes, yes.
you do the super abbreviated version of the Wolfram Schulte life story?
I was born in Germany, grew up in a very rural area that's called it's a Sauerland. The latest chancellor of Germany, Merz, is actually from the same area. So maybe
Oh.
that's the second famous person. I'm joking. Um, my father passed away very early in life. Social security at in the 60s wasn't well built out in Germany, and so my mom thought, well, the best thing that you could do is in some sense, give this son an education and good environment. And so she suggested, oh, shouldn't we in some sense have Wolfram go to a monastery, which was in some sense a boarding school and monastery. So their real objective was to maybe grow more monks and priests. And they were somewhat successful, but it didn't work for me. So I decided I wanted to do something else.
You could call yourself a DevTools monk or a database monk. I mean,
Yeah,
just a
yeah,
different
yeah.
field.
Yes, yes. I love that thought. Sure. And then what happens next is I wanted to get as far away from my hometown, that school, that environment as possible. And just the thought of it never occurred to me in 1980 to go abroad. So the furthest away in Germany was to go to Berlin because it was still, in some sense, in Germany, but far away. There were two borders in between. Then you have to cross into the East German Republic and out in order to get to West Berlin. So that's where I studied. I started with physics because I really love new stuff, and I didn't understand physics. And my professor said, "This is great. There is somebody who is in some sense eager to learn." But then I recognized everybody else understood physics, just not me. And then I thought, well, I should find something else. And then I walked through the university. I grew up in this monastery that had no computer, nothing. I walked through the university and ran into a lecture called Data Structure and Algorithms. And I was so fascinated that I decided to switch to computer science. So I had not programmed a single line starting studying computer science. And the lecture on data structures and algorithms was purely theoretical. So that was much closer to physics than what I do today. Cool. Really short, after having in some sense gotten my degree at the Technical University of Berlin, I did my PhD in compiler construction. So this brings me closer to the SQL world as I'm today. I went into a startup.
Back then, not that people still work on compilers, obviously, but I feel like probably as a percentage of attention, the compiler field was probably pretty center of focus. Is that fair to say?
Yeah, so compilers is one of the nice areas where theory and practice can work together. And that's what I really like. So coming from the theoretical part of physics, some says, oh, I can actually use my stuff. I can use algebra to optimize queries or whatever it is. And for parsing, we have in some sense lots of theories for how to generate parsers from descriptions that have certain properties. So that made it really, I think, is a it's a great area for exploration. It's maybe not so hip, but if you think about everything we do has ultimately run through compilers. So compilers are like an operating system, is one of the core components of our computer science stack, and therefore I think it deserves more love. And you see all the events that going on today with in terms of large language models and everything. They run on GPUs. How do you execute fastest on a GPU? Again, you need compilers. Compilers are at the bottom of everything.
Love it. Where does the story go from there?
Okay. So one interesting fact: 89 came the wall, the Berlin Wall came down. I was actually studying at the university. University is next to a mile next to the border. I had friends in East Germany and West Germany, and it's great to see. We see so much. I don't want to go into political turmoil. We see so much political turmoil. It all happened peacefully, and we came together as a country. So in some sense, that also impacted my life. So I'm not only a computer scientist, I'm also human. And so there are other stories that impact my life. After a short stint in a startup, I want to become a professor. I ran into a researcher from Microsoft Research in 1998, and he founded a group at Microsoft Research, and then he looked for people. And so I met him once at the conference. A year later, I got a one-line email from him and says, "Do you want to work at Microsoft Research? You could apply here." And so I did, and they accepted me. So I joined Microsoft Research in 1999.
Funny how those chance encounters can change your life.
This is also really interesting. The person is actually a famous logician, Yuri Gurvich. I asked him at this conference, what are the three most pressing problems that you feel? And he said, "Oh, yeah, I have this one, this one, this one." The next morning, I could answer two of him. And then I never heard from him again. After a year, when he sent me, "Oh, do you want to work at Microsoft Research?" So sometimes it's really good to ask people, what problems do you have? Because you can start thinking about it, and maybe there's even a job offer down the line. So that happened to me.
So it was 15 years, 17 years at Microsoft Research? How long?
Oh, it's 17 years. Yes.
17,
yes.
yeah.
And so Microsoft Research is in some sense like the Switzerland for all the Microsoft departments. So there's Office and Windows and Bing, each have in some sense their own business. And you are trying to, in some sense, be neutral. So never be too much on one side. And because you want to talk to everybody, it's not necessarily that all Office and Windows talked so well with each other. But as neutral Switzerland, as researchers, you can go everywhere. It was actually so interesting. They really liked what we are doing, but they never trusted us. So what does that mean? So I come up with ideas and, hey, you could do this one in order to improve product XYZ. And they said, "Oh, you're really smart. We like what you're doing, but it was not invented here." Or if this would be a service, we can't trust you. So at some point they asked me 2009 and then 2012 again, "Hey, can you build an engineering organization and help the Microsoft engineers with some of your tooling?" And that might be interesting. That story is also interesting. And so they gave me more or less a blank check that says I should report to their senior VP and figure out what's the thing that makes developers most effective. So I worked with Office and Windows before, and I recognize in some sense the slow iteration cycle because their builds were just too slow. If you want to change anything in the Windows driver, in order to test the Windows driver, you have to build all of Windows. That's hundred thousands of directories, each with tens of DLLs that all needs to be built. That takes hours, or Office, or Bing. And so what happens if you can build blazingly fast? So instead of hours, it's minutes or seconds. Then you can do many, many more experiments. And so we built this build system called Cloud Build. It's very similar like Google's Bazel. So it's distributed and caching. And that literally changed, in some sense, the organization inside how Microsoft is able to, in some sense, ship software so much faster. And it's not only good, it has actually several benefits. So in some sense, users stay in the flow, right? You want to do something fast and get immediate feedback. It also saves money because you are reusing artifacts that other people have already built, distributed caching over many users. And it's also even more efficient because we run it mostly on spare resources in Windows clusters. So in some sense, there are many things came together. If you build a great engineering system, you're really empowering people and you even improve morale. Right? It's not only about whatever. This is about excitement about your work.
I love that. We could talk about Microsoft for a long time, and we have in the past, but maybe you could take us forward to Facebook.
Very different culture, very egalitarian. There are no titles for engineers in Facebook. So everybody has the same title, which means is you can walk in everybody's office. And
is that still true today?
I think that's still today. So the managers have titles. Engineers, I don't know. Until 2021, when I left, they had no title. And I think that was an interesting view to, in some sense, have open flow of information and not being stifled by hierarchies. Nevertheless, people know what you have done, and so you get, in some sense, a label attached or a status. So I worked on a couple of projects, but at some point, somebody asked me, "Can you join the Facebook or Meta's data warehouse?" And and can you help us with, in some sense, call that janitorial work, clean things up? What's going on? We don't know. So I looked at it, and the interesting observation is everything is built for scale. So it's all world-class tools, but there is, in some sense, a database for time series databases, and there's a database for long-running batch jobs, and there's for ad hoc, and there's a database for cubing, and there's three databases for streaming. And so this is all wonderful, but if you want to move one workload from one engine to the other, you run into a problem. If you want to understand how all the dependencies in the warehouse work, you run into trouble. If you have maybe a bug detected 3 weeks ago and you want to make a backfill, how many different databases do you have to touch in order to, in some sense, get data back into a consistent state? So understanding data in Meta's warehouse and the processors, all the different SQL dialects and C++ binaries and whatever that's involved, and the AI workloads is really difficult. And so I joined when Cambridge Analytica hit Facebook. So when, in some sense, Facebook lost gave lots of private information away. And so until the time they were mainly doing manual tracking of PII information. But that doesn't work. And now you have such a heterogeneous system. So you have to stitch all the information together and with millions of tables. Automation is the only way to deal with it. So if you want to automate it, how do you label data and propagate it through the warehouse? It's one question. And the other thing is, how can you deal with all this heterogeneity? And then the observation is, oh, if we can build like a preprocessor for SQL, which we call UPM, and then that UPM can, in some sense, track the data, then each of these engines, we can still keep these engines around, but we do understand all the SQL that they are processing, and we can stitch all the information, how the information flows together. This became then the foundation of some of the work of the privacy framework that Facebook deployed. And it's good to know that your data is, in some sense, that somebody took care of your private data.
So we start to get closer to the topic that I want to spend most of our time on today. The tooling that you were involved in building at Facebook, there's a pretty natural bridge to the thoughts in your head that existed when you went to build SDF, and it's very related to the benefits that we want to bring to users. But in order to understand some of this stuff, I feel like it's important to understand databases at kind of a deeper level than I have had to personally. I've throughout my career been a user of a database, and it presents itself as an ODBC connection string and a SQL terminal. And I kind of don't. I mean, the whole beauty of it is I don't really need to care how the magic happens. But over time, over the last, I don't know, 3-4 years, there's been different reasons for data analysts, data engineers to understand more and more about the inner workings of a database. Like I mean, I had to go on a crash course about understanding file formats when Delta and Iceberg, and I'd never thought at all about how databases stored information. So the thing I'm hoping you can do with us today is track through the components of a database. And let's for a second just assume that the folks that are listening, they understand the idea of a database. They understand the differences between a transactional and an analytical database. If you haven't heard me talk about this stuff before, you can go back to this Michael Stonebreaker episode a couple seasons ago. We'll link it. So let's talk about analytical databases. What are the big components that if you were like a professor standing up in front of a lecture hall, like what are the things you would draw on the whiteboard?
Yeah, you know the database drivers, you're using ODBC to send queries into. So the question is, what happens with these queries? And so since I mentioned this, I studied compilers. So let me look through the glasses of a compiler builder how this thing works. So you send over the string, and the first thing is you have to interpret is this string actually a legal SQL string, or does it have the right UDFs? Does it have the right types? So you have to analyze in some sense the given string, and then you want to transform it into a representation that has nice properties. And then now we can go back into, in some sense, the history of databases where it come from. So 1970, there was in some sense Edgar Codd, who wrote a paper on modern databases using relational algebra. So just mathematics, right? And how could, in some sense, what are the operations on a matrix? Table is nothing than a matrix in order to do joins and projections and so on. So what happens even in most modern databases is that they translate the string representation into a representation over this funny algebra. And so then the nice thing that happens is in databases that, since it's an algebra, you probably remember from good old times, there's something like associativity laws. So if you have whatever 3 plus 4 bracketed together plus 7, it's the same as 3 plus bracketed 4 plus 7. So what does that have to do with this funny distribution? Oh, now you can change the join order. So meaning is, in your database, now you have a mathematical reason that, oh, you can use it, you can execute something this way, or you can execute it that way. And it makes it amazingly much, much faster. So you get optimization of 100 or 1000x faster by rewriting things. You can't do this in traditional programming languages.
This is part of the benefits of SQL being declarative. The programmer is not telling the database what to do, it's telling it the result that it wants. There must be some kind of, if you look at the Rust compiler, there's probably better and worse ways to run Rust code too, but the performance speedups are not quite as significant as you can get here.
Yes. That's correct. So even in Rust code, you write sequential, you write semicolon, one step after another. And therefore, the Rust compiler is not allowed to change the order. We just change the join order, right? And so that's the SQL compiler has much more ability to change things. And so if you now optimize, so the databases have this magic of the optimizer, and now ultimately you have to run it. And now what happens is, in the history of databases, that initially all databases had their storage baked in, because if you have a certain workload, you know exactly how to store it. But then what happened is, in modern big data, it's that compute and storage are separated out. So you have one independent representation for storage and independent compute. And so the latest effect was really, to separate engine from storage. So initially storage was part of the database, and now modern languages just use Parquet or whatever a representation they want. But the storage is really, really critical for performance again. So if you have, for example, ClickHouse, which is really great for massive scans and aggregate, they use a special, even for OLAP, a special representation in their storage layer. And that's why you can't move easily a data stored on ClickHouse and somewhere else, because they have their own special tricks. DuckDB has its own internal storage format. It can also work with external storage formats that are open source, but it works best with the internal storage, because engine and storage are, in the past, were always coupled, and now they're decoupled, but you still get benefits if you know exactly how things are stored internally. So 3 layers, in some sense: understanding, analysis, or 4 layers: analysis, optimization, execution with the parallel execution, and then the special storage layer.
You mentioned this a little bit in the explanation, but you said something about how databases used to be much more tightly coupled. Is it fair to say that the first relational database implementation was Oracle? Is that a true statement?
I think it was the first one that used SQL was IBM too, and then Oracle was soon after.
Got it. Okay. So just because I know Oracle better, let's say that we're back in whatever it was, like 1980 or something, right? That came
Yeah,
out.
yeah.
Let's say that we're back in 1980. You just buy Oracle. It's not like you don't have any choice of like how you compose your database system. You just like buy Oracle. You probably
Yes.
buy it on, I don't know, floppy disks or whatever. And today, I mean, you can kind of buy a database in the cloud and you get an API. You don't get floppy disks or anything else. You get an API. But there are also ways to interact with databases now where they're a lot more composable. When did this start being a thing?
The initial database were all, in some sense, transactional rated databases, row-based, and transaction managers are pretty difficult. So it's and then with the rise of big data, suddenly the OLAP, so the query database for analytical workloads starting to emerge. And then it was the first time hey, we should actually change the storage representation for OLTP. You have just the storage representation is rows and maybe trees for which we can in some sense do fast inserts and updates. But for OLAPs, you suddenly had the idea is, if everything is in some sense column based, then I can do a much faster accumulation of whatever happens in one columns, and I don't even have to read the other columns if I'm only interested in the maximum or sum over one column. So the existing storage technology from row-based changed due to the different workloads all up to column-based. And I think this is the first time when a major whatever representation suddenly shifts because of also different workloads. That's people start thinking is, hey, does that really have to be the same? And then we have Hive and Hadoop, which says is, actually, it can be different. We have MapReduce as, in some sense, as a compute representation, and we have a Hive distributed file system for storage. And so with big data, suddenly the separation of compute and storage fell apart.
So that's in like the 2008 era, something like that.
Yeah.
And so that was kind of the first time that things kind of got exploded out. There's no longer like one monolithic database system. You can see different workloads on top of the same HDFS file system.
Yes.
But now it's become even more diverse than that. Like if you go to the Velox site, you can bring your own many different things. Like you can bring calcite and substrate and etc. What does a modern database look like?
I think it's a great observation. So what happens is from these monolithic database systems, we become now modular databases. And why do you need a modular database? Because you have very, very different workloads, and sometimes you have to run 2 or 3 workloads. So the latest trend in databases is vector databases. What they are good for is for embeddings. So for machine learning scenarios, right? But you need you need a different architecture. You need a different storage. It's vectors. It's of high dimensionality. But on the other hand, all the data that you also use is in the database. So now you have, in some sense, scenarios that need many different things. So if you can compose, here is in some sense how you build. There's good examples. Maybe a simpler example is Postgres is transactional database, but currently
Postgres is everything all at once, right?
yes. But now the people try to, in some sense, run more analytical workload on it, and so they said, "Is can I actually use one of these composable engines and just take the analytical engine and let it work next to Postgres on the same data?" And now you get, in some sense, multimodal databases that can do two things: OLTP and OLAP, and they use different engines, but they have the same SQL. and maybe they have the same storage underneath. So this modularity now allows you to mix and match based on your workloads. What kind of engine do you want? What kind of storage system do you need? And by having a uniform storage representation like Iceberg or Delta Lake in between, and it's all open format, now you can plug different engines for different purpose, but they all speak the common language of here are my data, and here's the data, how the data looks like, and here's how I can update my schemas and my data. So it's I think it's actually a great time for all database researchers because you're not locked in, and also for all users because now you can more or less start mix and matching based on your needs, whether it's cost, whether it's latency, throughput, whatever you need. There's something out for you.
This world feels very compelling and interesting. It also feels kind of like it could be complex. I mean, you were describing the heterogeneity inside of the metadata environment earlier, and my guess is that increases the complexity involved in building native tooling that does all the things that you want it to do and all this stuff. But I think that this is not actually a very new idea. So right now, the industry is very focused on standards and open table formats and Iceberg, and CIOs and CDOs are like very much pushing in this direction. There's a lot of reasons to want to do that. But while this is a new development in the enterprise, by and large, it's not new for kind of the big digital native companies. Like this is what Facebook's infrastructure looked like a decade or more ago, right? You could spin up different types of compute all on top of the same lake back when you started there.
Yes. So I think is what one of Facebook's main enabler is that they very early on decided that they use the same storage representation, and there was HDFS and Metastore. And so with that, they got scale. At some point, even the existing, they had even to blow up their existing HDFS systems. But in principle, very early on, and therefore they could plug in different engines like Spark working on it or Presto working on it or other engines. And so that made it to have a stable base. Data is your stable base. The engines is in some sense what is much easier to change than moving monster data of that's in meta around.
And the thing that you need on top of that, the tables, is some level of confidence that if there's going to be multiple engines in there mucking around, that they don't step on each other's toes. And that's, I think, today the kind of the Iceberg REST catalog. It's like the thing that provides atomicity and all this other stuff. Like, was there a concept? Is this a concept that maps back to HDFS too?
Yes and no. I think is Iceberg took also learnings from how HDFS maybe didn't provide some of the core capabilities that you wanted. So in Facebook, you can, in some sense, guarantee isolation a lot with, in some sense, really smart scheduling that you don't step on each other's foot, right? So if you know that two people can write as long as they write to independent paths.
So it was the orchestrator's job.
Yes. So instead of pushing everything into the storage layer to guarantee isolation, there was lots of the storage layer didn't. I have to go back. Didn't guarantee as much isolation. It was much more, hey, smart developers and don't step on each other's foot, and smart schedulers guarantee that by design.
So one of the trade-offs, and you mentioned this before with the ClickHouse format, there's the benefits of standardization where everybody can kind of read and write the same thing. You can use heterogeneous engines. But then there is the optimization that you can do if you kind of tightly control the file format. Is this an either or proposition, or is there a way to have your cake and eat it too?
So what happens is that if you don't have any data, a database engine is of no use. It reads the data. So meaning is, where does the data come from? So even if there were proprietary engines, in the end, they opened up to ingest more different formats. And since there's pressure from the community, I don't want to, in some sense, maybe there's constant flow of new data in Parquet or in Kafka or wherever it comes from. We need to have, in some sense, native ingestion, at least native readers of other formats. And then for certain workloads, then you're in some sense also writers, because I think customers demand it. So I think it's all whether it's ClickHouse or hyperscale. Ultimately, everybody has to participate in the ecosystem because one tool doesn't cut it. And the way is to go with a common format. So it's not really wanted by all those players, but they have to adapt to reality and to customer demand.
There's a role to play for both engine-specific formats and open standards, because they both give you different things. The open standards give you interoperability, but for some use cases, like you could imagine ClickHouse being a part of an embedded analytics part of a product experience, and you're serving whatever large volumes of queries in real time, you're probably going to want to optimize for the file format that makes ClickHouse work the best. So it's not like we're moving totally away from a world where you just got one copy of your data and everybody operates on that.
Yeah, no. Whenever you deal with scale, so ClickHouse, where does it come from? Analyzing click streams. So how many events do you get? If there's 100 million people, in some sense, in Meta, clicking each 300 millisecond, in some sense, you get massive ingestion, and you need a special tooling for it. But then you provide aggregations, and where should the aggregations live? Maybe they can live again in just a Parquet file and can be used for other consumption. So I think it's really figuring out what your use case is, finding the right database technology, but not being boxed in. I think this is really, you want to have the way to, in some sense, connect everything from ingestion to consumption, because there are so many scenarios, whether it's retention, whether it's privacy, that really needs an overall view of your system and not only the highly optimized scenario that you're going after.
Okay, we've talked about a bunch of different engines at this point. I wonder if you could help us create some conceptual buckets for these types of engines. I'm not a super expert on the underlying technology here, but the way that my simple brain thinks about this is maybe there's like this Snowflake and BigQuery bucket. There's like the Data Fusion and DuckDB bucket, and then there's like this ClickHouse and Druid bucket. Do you think that are these like reasonable?
Yeah. No, I think you're spot on. So this is what each bucket, we can look at what are the characteristics of each bucket. So you start with Snowflake and BigQuery. In some sense, it's for big data analytics. These are columnar storage engines. They own their storage in order to optimize their workload. And meanwhile, they are opening up to, in some sense, other formats for ingestion and use. So Snowflake recently is able to, in some sense, I think, read iceberg tables, not write them, but that's only a matter of time when it comes. But there's really, in some sense, optimized for their scenarios. BigQuery the same. It's these systems really scale fantastically. You mentioned the other scenarios. That was DuckDB and Data Fusion. So we had SQLite is an embedded database for transactional load. So DuckDB sells itself as more or less SQLite, but for analytical warehouses. And I think it's a really nice ecosystem. It's so easy to integrate it into whatever your notebook that you can run now, local analysis. And so this is great. And I think there's lots of people excitement about it, but it's a single node engine. So if you think about big data, often it doesn't fit into a single machine's memory, despite the fact that we can ramp up. So there's still the need for the hyperscalers, the big data processors. Where's the difference between Data Fusion and DuckDB? DuckDB was really built for the user. So for ease of use, whereas Data Fusion is built and it sells itself as an embeddable modular data engines. So if you want to build a special purpose database, then, why don't you use Data Fusion and then add your special sauce to it? So Data Fusion is built for database builders and DuckDB is for database users, but it's both single engine. So that's why you see many more projects taken from Data Fusion and then build maybe the integration with OLAP on Postgres that uses Data Fusion and not DuckDB. And so
I, as a user, could I even download Apache Data Fusion and plug it into a Jupyter notebook and go to town? Or no, I have to.
Yes. I think you can, but it's icky because, for example, the Python it has Python bindings, but they are not as elegant and as well exposed. So in some sense, Data Fusion is really for the people looking inward to build new experience, but not from directly the use case of a user. You should just go to DuckDB and everything works out of the box. But then DuckDB has its own storage format. And so then the integration, if you wanted to change the optimizer in DuckDB, it's almost impossible. In Data Fusion, it's really, you can rip it out and plug your own stuff in. And so from that point of view, it's easier for database builders to work with Data Fusion and integrate it into new scenarios.
So I want to come back to Data Fusion. Can we hit our third bucket, the ClickHouse Druid?
Yes. And so ClickHouse is in some sense, it's just a combination of both, more or less, of the single engines and the other one. So ClickHouse is still a service that in some sense runs. But in Snowflake, if you really run distributed workloads, in Snowflake, you don't have to worry about how you distribute the data over the nodes. In ClickHouse, you have to give the ClickHouse more guidance on how they should do the sharding, so that there is some sort of more hand-holding to optimize the workloads. So it's not as easy as Snowflake or Databricks, but then it gives you this amazing capabilities for throughput that the others don't give you. So it's more hands-on and more narrow focused.
Do you see these three types of engines as in competition with one another, or do you see them as they all complement each other?
I think it's actually, I would rather like to see as complement each other. Big data says, if the data is really big, you can't in some sense, and the workloads is very diverse. You really need the scale of the cloud to perform, to scale up and down. And so I think there's nothing better. Clickstream I think is a special purpose solution for these high real-time streaming scenarios. And if you run a social platform and you get click streams, that's where the name comes from, then in some sense that's maybe the system to use. What we see with these single node engines, Data Fusion and DuckDB, we see that they want to grow up. So what happens is you can take a single node engine and now you can do the following. You can say, hey, that single node engine is actually often faster than Presto or Spark or whatever. So why don't I plug that single node engine as a leaf into a Spark cluster? So Spark runs in some sense the master that schedules all the work is still run in Java, but then now it schedules out in some sense worker jobs to Data Fusion. There's a project called Comet that is sponsored by Apple, where they try to make Spark faster by using Data Fusion as a component inside Spark. There's a similar project that uses Velox. It's a C++ code base inside Spark. Or there's another project from Mother Duck where they say, let's take in some sense, how can we use DuckDB, which is really fast, and work that in a more distributed fashion where we also have DuckDB workers on individual nodes that they have to coordinate work. So there's different models how these tiny engines want to grow to become competitive with the big ones, because the tiny engines are often newer than the other ones and they're optimized for certain workloads. And so they think they can have an edge compared to BigQuery or Snowflake in certain scenarios. But it's tough. I think it's all these technologies has been pushed to the limit, and I think engines also slowly become a commodity. So in some sense, if everything is in open source, if one person has a great idea, the next person can pick it up and he pushes it up. So the whole ecosystem grows, but there's in some sense.
You said something a second ago. So we started our conversation from 1980 and Oracle and IBM, and then we were tracking through the history of SQL databases, really. And then all of a sudden you said Spark. How do you bridge that gap? How does data fusion become an execution engine to something that is not SQL? I assume this has something to do with like your components of a database, and somehow Spark can plug into this.
Yes. Wonderful. I think so what happens is that in Spark, you can author your programs in data frames or PySpark or in Scala. But ultimately, what you build up is execution plans. And that's in some sense nothing than a logical plan. So when I come back to 1970 relational algebra, ultimately, all these engines internally, they build up a logical plan. And so ultimately, PySpark, when you execute it, at some point there's an intermediate representation of a logical plan. If you execute Scala against Spark, you build up a logical plan. And so this is actually now the common representation for all the databases. So now even data fusion written in Rust, that in some sense, if you can take that logical plan, I can in some sense go from one engine to the next engine and execute that logical plan on the other engine. And so there's maybe an interesting avenue. There's now trying, it's not yet clear whether it will succeed, not only have common representation for data formats, but also common representation for logical plans, so that you can take the input from one engine, analyze it, define a logical plan, and execute it on another engine. And so this is in some sense what the combination of Spark with data fusion tries to do, is combining these. And the intermediate language is called Substrate. So there's an emerging standard, DuckDB and data fusion supported, but not many others yet. So it's really just emerging. But that would now really enable us to compose engines with a common intermediate representation.
And for anyone who's listening and not watching, Wolfram is waving his hands around together in a motion that implies everything coming together.
yeah. Yes.
Okay, we've covered a lot of ground, and I want to kind of bring it all back together. And you and I haven't prepped for this. I haven't. I hate providing question lists to guests ahead of time, so I'll just hit you with it. There is a version of the world where SDF's technology, which really lives at the heart of everything that we've been talking about, gets integrated and used by all of DBT users. And at first, that experience probably doesn't feel that different. Or maybe, it's faster. Maybe there's some like good developer tooling that can be built on top of that. That's not to be underrated. That's important. But the future trajectory of what users of DBT plus SDF, what that will look like is very different than what the past has looked like. Can you paint a picture of that and draw the threads together from what we've been talking about?
We want to make developers more effective. I think this is at the heart, and then the second is also minimize operational costs of running all those things. But I'm really more concerned about the human. So sometimes keep you in the flow, make you more effective. If we really go very back, then we said, the first observation that in some sense was that people made is, if you just in an object-oriented language write a dot and you get IntelliSense. Now suddenly you don't have to go to in some sense a website anymore. Which functions are available? You get it at your fingertip. That's where, in some sense, the information should be. While you're typing, you get, in some sense, instant feedback. For SQL, it took a long time to get there, but we are there. So this is, in some sense, we're just catching up with SQL, which every other language has done. So now what's the next step? The next step is you actually want to say, hey, so now I have all my data, I have my models. Can I figure out that my data today actually looks very different than yesterday? And can somebody tell me that system is suddenly different? So today, in order to do this, you would have to write an outlier detection for in some sense, your particular data. But what if the system is so smart that in some sense it proactively tells you, oh, there's an outlier. Do you want to act on it or do you want to ignore it? So what if we can, in some sense, estimate where you are going? And it's like the dot. To have the dot tells you, oh, these are all the methods. Now you have, in some sense, the whole DAG, all the data, in some sense, all the description, all the tests, where things are going. I think this would be fantastic if we could go into that direction, much more predictive of where you're going. And if you think about whatever, initially we had, in some sense, oh, there's a single object in whatever TypeScript and the dot. So the context for that one is the single object that knows already all the methods that you can apply. Now you use LLMs. What is your context there? It's not only the single object that where your cursor is. It's actually everything in your models, your descriptions, your schemas, your types, maybe an additional glossary. So what can we now do? And we see this a little bit with text to SQL generation. But that can be so much more powerful if we really take that metaphor and move that forward. And so, do you have to decide what is your metric or dimension or whatever? If you look into the SQL, how it's being used so far, you could probably predict all of it. Right now, we ask users to put that in there. But why not ask the system, hey, I want to have metrics and dimensions. Which are the metrics and dimensions? And do I miss anything or whatever? So I think that would be a fascinating world for me.
And I'll add one more thing, and you tell me if you disagree with this, but the world that we've been talking a lot about, where there's different types of engines, and there's good reasons to want to use multiple of them because they have different properties. That world has already been here. The future's already here. It's just not evenly distributed, but it is becoming much more commonplace. And in that world, you want to be able to achieve that goal without exploding the complexity of your systems. And a world in which you can truly understand the SQL that users are writing and create logical plans out of that, it allows you to kind of think in a consistent way about all these different engines and how you interact with them. Is that a fair statement?
Yeah. I think this is right now the world is separated by dialects, but wouldn't be nice to have, in some sense, a common understanding? And so there is already one that's just inside the database, that these logical plans that knows exactly everything. So the question is, how can we make that more accessible and usable? And so that in some sense you can freely move from one engine to the other. And the system tells you, oh, by the way, whatever, your drone behaves differently on this engine. And that's why you have to adapt your program like that if you wanted to run it on a different engine. So one thing is to bring all the systems down to one language. This is in some sense what they tried with standardization, but since there are so many different scenarios and variations in SQL, I don't think that in some sense
you're not going to get everyone to agree to
back to whatever a tiny kernel will not work. I think we will have to live with the fact that there are many dialects good for different capabilities, but you still want to move from one to the other, and enabling that ecosystem, I think, would unlock so many opportunities for a different developer experience, different cost profiles, different throughput scenarios.
Amazing. We could talk a lot more about this, but I think we've got to leave it there for the moment. Thank you for hanging out, and to listeners for whom this has been an interesting topic, we will have more to share with you soon. Thanks, Wolfram.
Yeah, thanks a lot for the invitation and inspirational for the opportunity to explore this space with you.
The Analytics Engineering Podcast is sponsored by DBT Labs. I'm your host, Tristan Handy. Email us at podcast@dbtlabs.com with comments and guest suggestions. Our producers are Jeff Fox and Dan Poppy. If you enjoyed the show, drop us a review or share with a friend. Thanks for listening.